So we worked out that the Julia set for the function z squared is the unit circle. So that's the simplest case for which we can compute the Julia set. We're going to try the second easiest example, Julia set for z squared minus 2. It's already challenging, so here we go. Okay, so we're going to look at Julia set for z squared minus 2. Note that to understand the Julia set, we want to understand the boundary of the basin of attraction for infinity. All right. So we have to understand the iterates. If you start computing the iterates, I've done so here. So this is the first function. If you iterate it, that's what you get when you FOIL it out. And then probably the third step is, as far as I'm willing to go, as far as computing the expansion and the polynomial itself. I don't quite, maybe there's a pattern, but it's kind of complicated. So this doesn't allow us to get very far as it did for the case of just z squared. This constant term is just going to add more terms, and every time we square, we're going to get so many more terms that it becomes unbearable computation. So we're going to use a trick. And it's a trick that we've already kind of seen before. So remember when we had a polynomial of second degree, we used a function and its inverse and kind of sandwich this with a particular quadratic function. And we were able to compare that, well, the long-term behavior is similar for these two cases. And we reduced the complexity of the problem. We're going to try to do that again, except this this companion function that we're using here is a little bit trickier. So let's try to understand what's happening here. Okay, so we're going to use this function phi. We're going to look at the domain of outside of unit circle. So we're going to use almost all the complex plane except outside of the unit circle. And we're going to map to almost all of complex plane except for the interval between -2 and +2 on the real axis. So along here, we're not going to map to it, but everything else will get filled in. Okay, so I'm claiming that this function phi does this. And our function looks like w plus 1 over w. And this w here is a complex number, of course. So let's try to see this. I think the way to best see it is to not look at like a particular point on the complex plane, but look at rings of numbers instead. So imagine we pick a radius that's larger than 1, and we're going to see what this maps to. So just as a spoiler, I'm just going to say it's going to map to ellipses that look like these. Okay, so how could we see that? Let's do that. So we're going to write down w in polar form. R times e to the I theta, and R is going to be strictly greater than 1 here in the input. Okay, so let's compute it. So phi of w is going to be r e to the I theta plus 1 over r e to the I theta. r e to the I theta plus, I have 1 over r here. And 1 over e to the I theta is same thing as e to the negative I theta. So I'm just going to rewrite it that way. I'm going to use Euler's formula. So r times cosine theta plus I sine theta plus 1 over r times cosine of, well, cosine of negative theta is same thing as cosine of theta because cosine is an even function. And sine of theta is same thing as negative sine theta because sine is an odd function. So the negative up here could be pulled outside of the sine function, like so. Okay, and then here I'm going to collect the real terms and collect the imaginary terms together. So r plus 1 over r cosine of theta, that's the real part. And r minus 1 over r. That's the imaginary part. Now, if I kind of hide this portion, so there's some scaling factor in front of the cosine and sine terms. If I didn't have that in this expression, this would be a unit circle because cosine theta plus I sine theta traces a unit circle in counterclockwise direction. So what this does is that it stretches the horizontal component by factor of r plus 1 over r, and it stretches the vertical component by r minus 1 over r. So you can kind of already see that it started with the radius of 1. R plus 1 over r is going to be slightly larger than r because it's r plus something and r is positive. And in the vertical direction, it's going to get squished a little bit. It started with the radius of r, but we're now subtracting negative 1 over r. Okay. So what does this do? So I think maybe we could just kind of look at the graph of r plus 1 over r and see what that looks like. Okay, so I asked the Google to graph it for me. Let's see. This doesn't show me enough, so let me zoom out. Okay. Right. So this is the graph of r plus 1 over r. Note that we're plugging in only radius greater than 1. So from 1 on, this function is increasing. Okay. And also, I guess when r is exactly equal to 1, then y value is exactly equal to 2. Okay, so let's see if we can go back to the notes. Okay, so I've said the horizontal portion. So the smallest the horizontal portion could be is 2 units. It doesn't quite reach 2 because our radius r doesn't reach exactly 1, but it gets very close. And the y stretch factor, we should have graphed that at the same time. Okay, so let me graph r minus 1 over r. Okay, and then zoom out. Okay, so now you can see that, right, it's also an increasing function with r. And when r is equal to 1, this is exactly equal to 0. and then it gets larger and larger. Let's jump back to the picture. And hopefully this picture of phi mapping makes sense now. We have rings of larger and larger radius. It's going to be mapped to ellipses in the image where the semi-major axis starts at 2 and gets larger and larger. And the semi-minor axis, the vertical radius, is going to be starting close to 0 and then increasing as r gets larger. So all the circles maps to ellipses of this type. Okay, I hope that made sense. All right. Okay, so we have this function phi. How could we use this guy? Let's see if we can look at the mapping. Okay. Okay. So we want to look at this combination phi inverse of f of phi. So what we're going to do is we're going to look at maps from outside the unit circle. And we know that we just checked in the previous page that maps to all the complex plane except for the interval from -2 to 2. And from -2 to 2, we can look at the function f. So remember, the function we are looking at is z squared minus 2. And I should note that I mean, if you graph the real function, okay, between -2 and 2, the image maps to any real number from -2 to +2. So it maps that interval to itself, right? So this part that it's not defined, the domain, maps to itself. Everything outside of that is mapping to outside of that. Okay, and then we're gonna undo the function phi inverse and then go from this complex plane minus that interval to outside of the unit circle. So we're gonna take this very complicated 3-step process and then end up with this function g that maps from outside of the unit circle to outside of the unit circle. So the payoff is that we discuss complicated functions, but the function g is actually very simple. We reduce this to a simple function. So the claim is that this map is g, where g is the square function. So we could prove this, but the inverse is a little bit difficult to write down. So instead, what we could do is we could just take the phi of both sides and instead prove f of phi is equal to phi of g. So that's what we'll prove instead. That's a lot simpler because the phi function is easier to write down than its inverse. Okay, so let's check that. So f of phi is going to be f of the phi function here, and phi was w plus 1 over w. And then the function f is taking the input, squaring it, and subtracting by 2. So we could FOIL this out. We get w squared. The cross term is going to be w times 1 over w, which is 1, and there's 2 cross terms. So that's where we get the 2. And finally, 1 over w squared there. We carry over the -2 on the outside of the square. Conveniently, 2 cancels out. And then we have w squared plus 1 over w squared. This is exactly the function phi when you plug in the input of w squared. So that's phi of g. Okay, all right. So that was a complicated detour, but basically this is saying that if you understand what g does, which we do, we know the iterates of the z squared function, or I guess in this case, I'm writing as w squared function. We computed the Julia set for that, right? It was the unit circle. Okay. So therefore, if we look at the complex number, complex plane minus the line segment from -2 to 2, this function f behaves like the square function outside of the unit disk. Right? So what we really want to try to understand is what's happening with the function f and iterates of f. But that behaves in a similar way because we know that f to the nth power, oh, actually, yes, sorry, not the power. Nth iterate of g is same thing as nth iterate of f, except we sandwich it with those two phi functions. So if this behaves like everything outside of the unit circle blows up to infinity, that translates to everything outside of this line segment from -2 to 2 blows up to infinity. So the only thing that doesn't blow up to infinity is this line segment from -2 to 2. Okay. All right. So what do we know now? So we know that the basin of attraction for infinity is everything outside of the line segment from -2 to 2. Therefore, the Julia set is the boundary of that domain, which is the line segment from -2 to 2. So it's Julia set is a line segment. We have figured out 2 Julia sets so far with some difficulty, right? Julia set for z squared is the unit circle, and the Julia set for z squared minus 2 is the line segment from -2 to 2. Now, you're probably disappointed with this video. We haven't got to any cool fractals yet. But here's the kicker. It turns out that these are the only 2 Julia sets that look simple like this. Every other Julia set is absolutely wild looking. They're all fractals, very intricate structures. So we will get there in the next video.